So we are in the week 6 and this is a live interaction session second. So in this session we will solve the GATE previous year question mainly focusing on the municipal solid waste management. So beginning with the first question which came in GATE 2022. So at a municipal waste handling facility, 30 metric ton waste of food waste, yard waste and paper waste was available. The moisture content of this mixture was found to be 10%. The ideal moisture content for composting this mixture is 50%. The amount of water to be added in this mixture to bring its moisture content to the ideal condition is. So so they are asking at the end that the what how much water they need to add to get ideal condition of for composting is 50%. So let's first write the given data. So 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 wet waste, so we know that moisture content is equals to wet waste, weight of wet waste minus weight of dry waste divided by the weight of wet waste into 100. So now from the question they have given some weight, that is 30 metric ton mixture of food waste, yard waste. So in this 30 metric ton of food waste, yard waste and paper waste, so basically it is a wet waste because they have given the moisture content of this mixture was found to be 10%. So it is, we will write 30 minus dry weight we are yet to calculate, and again here 30 into 100, and the moisture content they are talking about is 10%. So it is 10. Now if you, so basically we can write it this way: 30 minus dw by 30. So if you uh, solve it, dry weight dry weight of the waste will be around 30 minus 3, 27 metric ton. Since the question have asked, they have given the unit as metric ton. Now they are asking the ideal moisture content for composting this mixture is 50%. The amount of water that need to be added. So now this is a dry weight. Okay, on adding water to this dry weight, on, so the dry weight will not change. So on adding water to municipal solid waste, obviously this is the dry weight of the waste will not change. Okay, so now the moisture content is wet waste, we know this. Now dry waste is 27 metric ton and divided by wet waste. So moisture content for ideal composting is given as 50%. So this into 100. So 50%. So we can write as 0.5 wet waste minus dry weight and the weight of wet waste. So basically, when I am saying this wet waste, weight of wet waste, it is the new wet weight of municipal solid waste when moisture content is increased to 50%. Okay, so this is the that wet weight. Now here weight of dry weight we know 27 metric ton. So 0.5 is equals to minus 27 divided by weight of wet weight. So if you calculate, you will find that the weight of the wet waste will be 54 metric ton. Okay, but this is the ideal uh, condition, wet waste when the ideal moisture content of the composting mixture is 50%. But the question is asking the amount of water to be added to the mixture to bring the moisture content to the ideal condition in metric ton. So initially they had this mixture. Okay, this was the wet waste. Now for ideal condition, we got the wet waste is 54 metric ton. So next, anyone has? Yes, correct, Vinod. So now it will be that extra amount of water added in municipal solid waste to bring its moisture content to ideal condition. It will be 54 minus 30. So we will get 24 metric ton. Okay. Anyone has any doubt? So basically in this, so I will just summarize this question once again. So they have given a mixture of waste and they have given their weight of that mixture of waste 30 metric ton, and then they are selling that, then they are telling that that mixture has a moisture content of 10%, but for composting they need ideal moisture content of 50%. So how much water they need to add in that waste to get the ideal condition? So initially we know the formula of moisture content. Using that we calculated the dry weight. After calculating the dry weight, so then we calculated the wet weight after when the ideal condition is 50% moisture content. So this way we calculated the wet weight. So then for extra amount of water that need to be added in to bring it moisture to ideal condition will be 54 minus 30, is 24 metric ton. I hope this is clear now. So let's move to the next question. So in this question they are saying in a city the chemical formula of biodegradable fraction of municipal solid waste is C100 H250 O80 and N. The weight the waste has to be treated by forced aeration composting process, for which air requirement has to be estimated. Assume oxygen in air by weight is 23%, density of air is equals to 1.3 kg per meter cube, atomic mass carbon is equals to 12, hydrogen is 1, O is oxygen, O is 16, N is 14. C and H are completely oxidized, whereas N is converted to ammonia during oxidation. For oxidative degradation of 1 ton of the waste, the required theoretical volume of air will be. So basically, they have given some biodegradable fraction waste formula, that is C100 H250 O80 and N. Okay, so now they are telling that C and H. This line is very important. C and H are oxidized completely, where N is converted only into ammonia during the oxidation. So now, if you degrade it for oxidation, in presence of oxygen, it will produce CO2 plus H2O plus ammonia. Why I wrote this ammonia? Because they are telling C and H are oxidized completely, where N is converted only to this ammonia during the oxidation. Okay. Now we have to balance this. First, you can see C is here 100, so here it will also become 100. Okay. So H is 250. Okay. So H is here as also. So how we can balance it now? So like for H, balancing H. Okay. So left hand side how much it is? 250. Okay. 250 is equals to right hand side how much it is? Suppose here I kept X. 2x plus 3. So X will come out to be 123.5. So now I can write this. Uh, so now I can write this as 123.65. 123.5. Okay. So this H got balanced now. So if you calculate it, it will be equivalent on both sides. So now for the oxygen. So here you can see, here it is 80, here it is O2. Okay. So let's suppose here it is Y. So 80 on LHS. Okay, this is 80, then 2Y is equals to, now here again O is there, that is 200, plus again O is here, so plus 123.5. So if you solve this, the Y will comes out to be 121.75. So then we can say 121.75. Okay. So just it was not. So it is basically, here we can write 121.75. Okay. So now in the next slide I will write the complete equation. So it so from there it will be easy for you to follow up. C100, H250, O was how much? 80N. 80N plus 121.75 O2, giving 100 CO2 plus 123.5 H2O plus ammonia. Okay. So this up till here, I think is it clear? Up till that point, is it clear? Anyone has any doubt? Amit, Binoy?
No, sir.
Okay. Now the question says, so once we have first important point in this question is, first you have to write the equation and then you have to balance it properly, else you will get a wrong answer. Balancing, okay. So now the question says, for oxidative degradation of 1 ton of waste, the required theoretical volume of air. Okay. So see, if you calculate the molecular weight of this, it will be near to around 2744, and if you calculate this, it will be around 3896 gram. Okay. So now simply we have to apply a unitary method where for 2744 gram of municipal solid waste requires 3896 gram of oxygen. So for 1 ton basically 1000 kilogram. Okay. So for 1000 kilogram, it is required is 3896 divided by 12744 is equals to 1000. So you will get around 3896 divided by 2. So you will get around 1419.825 kg. Okay. So this much amount of oxygen is required. So we, for the purpose of this, to calculate the oxygen required. Now question says one more thing. So there is one more twist. So the thing is, they are not asking about the oxygen, they are asking regarding the theoretical volume of air. Okay. So here is the theoretical volume of air. In the question they are mentioning, assume oxygen in the air is 23% and density of the air is 1.3 kg per meter cube. So from there we can say, so 1.3 kg of air, 1.3 kg of air contains, so based on the question, 23%. Okay, so 0.23 into 1.3, which will give out to be 0.299 kg of oxygen. Okay, therefore if 1.3 kg of air contains this much amount of oxygen, so we can write it in other way also, like 0.299 kg of oxygen is present in 1.3 kg of air. Like reverse I wrote, 1.3 kg contains this much oxygen, so I can say this much amount of oxygen is present in 1.3 kg of air. So now I wrote it in this way because here we have calculated the oxygen requirement. So 1419.825 kg of oxygen will give 1.3 divided by 0.299 into 1419.825 kg of air. So if you solve this, you will get 6173.152 kg of air. Okay, so now this is the in kg we have got, and question again there is a thing they have asked in meter cube per ton. So for this we have to do, so volume of air. So we know that density is equals to mass by volume. For volume it will be mass upon density. So mass we just now calculated to be 6173.52 kg. 6173.152, and density is 1.3. So if you solve it, you will get 4748.57 meter cube. This is the answer. So anyone has an, yes. So anyone has any doubt? So I will just again explain this question. So in this question they are telling, so in a city the biodegradable fraction of municipal solid waste is this much, C8, H250 and 8. So the waste they are telling is to be treated by the forced aeration composting process, for which air requirement has to be estimated. Assume oxygen in the air is this much, 23%, and density of air is 1.3 kg per meter cube. So after that they are writing, carbon and hydrogen are oxidized completely, whereas nitrogen is converted only to ammonia during oxidation. For oxidative degradation of 1 ton of waste, the required theoretical volume of air in meter cube per ton will be. So to solve these kind of questions, it is very important to first write the equation. Once you know what will be the equation, then you can balance it. So here the equation says C100 H250 O80N in presence of oxygen will produce CO2, H2O and ammonia. Ammonia because they have mentioned it here, and is converted only into ammonia during oxidation. So once you have written the equation, then you can balance it. We balance the H and hydrogen and the oxygen. After balancing, we just applied a unitary method that this much amount of waste requires this much amount of oxygen. So for 1 kg of waste which is asked in the question will require this much kg of oxygen. Okay, but in question they are asking in terms of meter cube per ton volume. They are asking, they are not asking in terms of mass. So since we know the total volume of oxygen that will be required to oxidize the 1 ton of waste, so huh, So after knowing this, we should know the amount of oxygen present in the air. In the question, it is saying that the oxygen in the air is 23% and density of the air is this much 1.3 kg. So basically, it means 1.3 kg of air contains this much amount of oxygen. Or in other way, we can write it like this: 0.299 kg of oxygen is present in 1.3 kg of air. So when we know this thing, we can, so from the total mass which we got, total weight from which we got from the this in this slide, so this much amount of oxygen will be present in how much amount of air? So this much amount of oxygen is present in how much quantity of air? So this is the total quantity of air. But the question is asking in volume. So using that volume density, we calculate the volume of air. So this is the final volume of the air. I hope this is clear. Now let's come to the next question. So the next question says a waste activated sludge is to be blended with green waste. The carbon and nitrogen content per kg of waste activated sludge and green waste on dry basis are given in the table. The ratio of waste activated sludge to green waste required to achieve a blended C by N ratio of 2:1 on dry basis is. So this is a very simple question. So in this thing, how we will write? So basically total carbon content. Okay, let's start in the next slide. Total carbon content will be. So from the figure they are mentioning carbon in waste activated sludge is 54 gram and in green waste it is 360 gram. So similarly they are mentioned about the nitrogen and they are asking what will be the ratio to be blend in a C1 ratio 2:1. So total carbon content will be 54 WAS 54 WAS plus 360 GW. Okay. Similarly, total nitrogen content will be 10 WS plus 6 DW. Okay. So now if I do C by N ratio, which is how much it is required? It is 20 to 1. So we can write C by N ratio required is 20 to 1. So total carbon is how much? 54 WA waste activated sludge plus 360 green waste divided by total nitrogen content is 10 waste activated sludge plus 6 green waste is equals to 20 by 1. Now if you solve this equation, if you solve this, now simply you can solve it. If you solve it, you will get WAS by GW to be 1.644. Okay. So anyone has any doubt in this question? Anyone has any doubt? Okay. So okay. So we are done with third question. So next starts the another question. So in this question, they says a city generates 40 into 10 to the 6 kg of municipal solid waste per year, out of which only 10% is recovered and recycled. The rest goes to landfill. The landfill has single lift of 3-meter height and is compacted to a density of 550 kg per meter cube. If 80% of the landfill is assumed to be municipal solid waste, the landfill area required would be. So the answer will be, so see this question. In this we should first know that compacted volume of municipal solid waste VC is equals to amount of municipal solid waste going to landfill divided by compacted density. Similarly, like if you look at it, it will like compacted density is equals to mass by volume. Since I need to write volume, I just replace with like compacted density in numerator. Okay, so amount of municipal solid waste going to landfill is how much? 40 into 10 to the 6, out of which 10% is uh, recycled. Okay, 40 in, so okay. So now you see the amount of waste goes to the landfill is total amount of waste is this much. So if 80% of the landfill waste is assumed to be the municipal solid waste. So since 80% 0.4 into, okay, there is some issue in data I think. So okay, we will do this question. So I think some data is missing. 30 city generate 40, out of which only 10% the landfill area would be. So uh, here some, I think some error is there in this question regarding this 40. Okay, we will solve the next question first, then we will look at what to do in that. So the next question, let's start. The amount of CO2 generated while completely oxidizing 1 kg of CH4 to the end product. So this is set to, okay. So the amount of CO2 generated while oxidizing 1 kg of CH4 to the end product is. So in this question, basically what we have to do, first CH4 we know if gets completely oxidized, it produces CH4 plus O2 and it produces CO2 plus H2O. So if you balance it, it will be 2H2O. Okay. So we know that the molecular weight of, so here the molecular weight of CH4 is 16 gram, that we know, and the molecular weight of CO2 is 44 gram. Okay, so we know CH4 plus O2 produces CO2 and H2O. So amount of CO2 generated, to know amount of CO2 generated in in kg. So the question is in kg. So we can say 1 mole, based on the equation you can see 1 mole of CH4 gets completely oxidized and forms 1 mole of CO2. So you can write 1 mole of CH4 gets completely oxidized and formed 1 mole of CO2. Okay, so now 1 mole of CH4 gets completely oxidized and forms 1 mole of CO2. So we can say this way also. So 1 mole of, so Since here you can see 1 mole of CH4 gets completed from 1 mole, so and molecular weight of CH4 is 16 grams, so we can say 16 gram of CH4 when gets oxidized and produces 44 gram of CO2. So 16 gram of CH4 leads to formation of 44 grams of CO2. Okay, so now for 1 gram it will be how much? It will be 44 divided by 16. Okay, this much gram of CO2 will be produced, but in the question they are asking not in per gram, in kg. So it for 1000 gram, basically 1 kg, so 1000 gram it will be 44 divided by 16 into 1000. So now you got 2750 gram. So again, see, there is a twist. We got till now in gram, we should get in terms of kg, because the question asking in kg and for completely oxidizing 1 kg of CH4. So since our question we answer we have to report in kg, it will be 2.75 kg. Okay. Anyone has any doubt in this question? Anyone has any doubt? So let's move to the previous question. Yes. So city generates this much amount of waste, out of which 10% is recovered and recycled, and rest goes to landfill. If 80 landfill has this much height, has a single lift of 3 meter height and is compacted of 550 kg per meter, 80% of landfill is assumed to be municipal solid waste. Landfill area required will be. First of all, the compacted volume of municipal solid waste is equal to amount of solid waste going to landfill and compacted density. Just this thing I simply wrote by density is equal to mass by volume. So if I have to keep everything in terms of volume, it will be mass by density. Okay. So now we have to calculate the amount of municipal solid waste going to landfill. Okay. So see, they are asking a city generates 40 into 10 to the 6 kg of municipal solid waste, and only 10% is recovered and rest goes to landfill. This sentence is very important. Rest goes to landfill, only 10% is recovered. So that means if 10% is recovered, so 90% is going to landfill. So that's why 0.9 we have to multiply. So we will get the value of 36 into 10 to the power 6 kg per year. Okay. So now we know that the amount of municipal solid waste going to landfill, 36 into 10 to the 6 kg per year. So compacted volume now will be, because we know that the compacted density is 550 kg per meter cube. So compacted volume will be 36 into 10 to the power 6 divided by 550 kg per year. Okay. So be very cautious about the units. So if you solve this, you will get 65454.54 meter cube per year. Okay. So this is the compacted volume. Now the question says, so but we have to calculate the landfill area. So now the question is, 80% of landfill is assumed to be municipal solid waste. So we can say that the volume of municipal solid waste is basically 0.8%. 80% means 0.8 into total landfill volume. Okay, so because in the question they are mentioning it 80% of landfill is assumed to be municipal solid waste. So that means what? That the volume of municipal solid waste is 80% of total landfill volume. So we can write it like that. For calculating the total landfill volume, so I am representing it as TLV. Total landfill volume will be is equals to volume of municipal solid waste divided by 0.8. Okay. So volume of municipal solid waste how much? Just now we calculated the compacted volume. So 65 0.8. So if you calculate this, it will be 81818.18 meter cube per year. That is the total landfill volume. Okay. Now, but in question they are asking the only the landfill area. So to calculate the landfill area, what we have to do? Area of landfill required is equals to volume of landfill divided by height of landfill. Okay. So now volume of the landfill we calculated as 81818.18 and height of the landfill they have given in the question as 3. So say single lift of 3 meter height. So every word is important in a question. So if you divide it by 3, it will be 27272.72 meter square. Okay. So the answer will be 27272.72 meter square. So this was the solution. So anyone has any doubt in this question? Yes, correct, Binod. So I will summarize the today's session. Okay. So initially we started with the question which came in GATE 2022 and it was based on the moisture content. So moisture content we in the question they have given the moisture content and they have given some ideal ratio for composting mixture. So first we calculated the first we write the equation of moisture content, then we calculated the dry weight. Okay. So after calculating a dry weight, we the once we calculated a dry weight, then since the question says that the ideal moisture content for composting this mixture is 50%, so we then calculated the new wet waste of municipal solid waste, when the ideal moisture content will be 50%. Okay, so from that we initially then we use the value of the dry weight to calculate the new wet weight of the municipal solid waste management when moisture content has to be 50%. So then after calculating the new wet waste, so since extra amount of water the in water added in moisture to bring its moisture to ideal condition will be 54 minus 32 because initial moisture content was this, but to bring the moisture content for the in the range for composting, so it will be 50, it was 54. So that means that much extra amount of water was required to get added. So then we proceeded with the next question where they have given some formula and in that they have told that the waste has to be treated with forced aeration composting process for which air requirement has to be estimated. And then they have given the data regarding C and H are oxidized completely, where whereas nitrogen is converted only to ammonia during oxidation. Based on the given data, we formed our equation. After the equation, the first thing what we did balancing. Once we are done with the balancing, we just wrote the unitary equation, like this much amount of waste required this much amount of oxygen. For 1 ton of waste will require this much amount of oxygen. But in the question, they were asking in terms of theoretical volume of air. So to theoretical volume of air, we first calculated the in air how much quantity of oxygen is present, and by knowing that the amount of oxygen that is present in the air, we calculated that this much amount of oxygen then will be present in how much quantity of air. After knowing this quantity of the air, we calculated the volume of air. Uh, we calculated uh, we calculated the volume of air, which was 6173.152 divided by 1.3, that is the density, and we got this much volume of air that is required for the degradation of 1 ton of waste. So for degradation of yes, this much amount of waste. So another thing, then we solved one question which was based on the C by N ratio. So in the question, they have given us the parameter carbon and nitrogen, and they have given that in waste activated sludge and green waste how much their concentration is, and then they are asking that the ratio of waste activated sludge to green waste required to achieve a blend of C by N ratio is of 2:1 ratio on dry basis is. So we know that the total carbon content in both the waste and total nitrogen content in both the waste. Then we applied the C by N ratio required is 2 and T is to 1. So we just wrote the total carbon content and total nitrogen ratio. After solving this, you will get weight activated sludge by GW green waste is 1.644. Okay. So then our next question was this one. So in this question, a city generates 14 to 10 kg of meter cube of waste, and in this question basically they are asking the landfill area depending upon the waste generated and how much waste is going to the landfill. So what we did first, we first calculated the compacted volume of municipal solid waste, that is which is equals to amount of municipal solid waste going to landfill divided by the compacted density. So then how we calculate the amount of municipal solid waste going to landfill is that in question itself they have written that this is the total amount of waste that is generated, and from this total amount 10% is recovered and recycled and the rest goes to landfill. That means 90% of this waste is going to landfill. So we wrote 90% of this much. Okay, amount of waste going to landfill we calculated by multiplying the total amount of waste with 0.9, that is 90%. Then we calculated the compacted volume. When we call After calculating the compacted volume, so this was the compacted volume. Okay. Then we calculated then in the question it was written the volume of municipal solid waste, that is the total landfill volume is filled with the 80% of municipal solid waste. So we can write the volume of municipal solid waste is 0.8% of total landfill volume. Then here we calculated the total landfill volume. Now we have to calculate the area of the landfill A. So how we calculated? So volume of the landfill divided by the height of the landfill, and this way we calculated the landfill area. Okay. So now coming to the next question. So next question talks about amount of CO2 generated. So they are asking in terms of kg. This line is very important. While completely oxidizing 1 kg of CH4 to the end product. So we just wrote the balance equation, that is CH4 plus O2 is equals to CO2 plus 2H2O. The molecular weight of CH4 is 16 gram and molecular weight of CO2 is 44 gram. We know 1 mole of CH4 gets completely oxidized and form 12 mole of CO2, which is obviously visible in this equation, that is 1 mole of CH4 when completely oxidizes produces 1 mole of CO2. Okay, knowing this, what we did, since 1 mole react of CH4 produces 1 mole of CO2, that means 16 gram of CH4 is producing leads to the formation of 44 gram of CO2. So we applied unitary method, that then for how much it will be for 1 gram, and then in question they are asking about in kg for 1 kg. See, here they are mentioning while oxidizing 1 kg of CH4 to the end product is. So for 1 kg of CH4 basically means 1000 grams. We calculated as 2750 grams, but in kg it will be 2.75 kg. So yes, is it clear? And few things which I will mention apart from these questions is, so so there are three principal methods for landfilling dry areas. So these are just short information. You should know this in municipal order because in gate they can ask this kind of question. The first is the principal method used for landfilling dry areas may be classified as, first is area method. Okay. Second is trench method. Third is depression method. Okay. So also, so since these are landfilling methods, okay, now for the composting, two methods of composting, which is generally adopted, is, first is indoor method, and second is Bangalore method. Okay, so this was very important. It is, you should know about this Bangalore method and the indoor method. So, and apart from this, there are few things which is important, is like uh, garbage. What are the different types of waste, classification of different types of waste. See, garbage basically it is a all sorts of uh, all sorts of putrescible organic waste. BLE, putrescible organic waste. So this is over all sorts of putrescible organic waste. Okay, which includes putrescible waste which can be decayed, like whatever obtained from kitchen, hotels, restaurants, and like examples are vegetable peelings, food waste. Okay, fruit peelings. So that we call as garbage. Second thing is refuse. There is a difference between the sorry, not refuse, rubbish. Rubbish. Okay, there is a difference between the garbage and the rubbish. It includes all non-putrescible waste. Okay, so in these examples are rags, broken pieces of glass, furniture, cardboards. Okay, so this is very important. You should know about it. And another thing is ashes. Ashes basically means it's the incombustible waste product. Incombustible waste products from hearths and furnaces. Okay, so this you should know. And apart from this, uh, another basically is types of solid waste. Types of solid waste. So basically, first is municipal solid waste. Second is industrial waste. Third is hazardous waste. Okay, so it is very important for you to learn all these things. And so this is all about today's session. So also it is important. Also, other thing, other one other point is, so this I have mentioned. Another thing, the gases which are found in the landfill includes. So question can come in any form from these things. So gases from the landfill includes CO2, carbon monoxide, ammonia, hydrogen sulfide, okay, nitrogen gas. Most common is methane. This is very common because you can every day you might be hearing like in summer season that there is a landfill fire. So this is because of methane only. So better remember all these things, and others are uh, oxygen, sulfide. These are the major things that you should remember. So basically, out of these two, first main is CO2 and methane. These are the principal gases. Principal gases. How they are produced? From anaerobic decomposition of organic solid waste. Okay. So yes, this was all about today's session. So all these things you should remember it. And So this is all about. Thank you. So if you can want to leave, you can please leave. If you have any doubts, you can ask.